All right. All right, everybody, welcome to another episode of Zed Decoded. Today we're going to talk about the rope, the data structure rope. So I have with me the three co-founders of Zed. They're writing their messages here. So we have Antonio, Max, and Nathan. And before we start, I want to set the scene a little bit for everybody who doesn't know what a rope is. Imagine you want to build a text editor. What's at the heart of a text editor? Text. How do you represent text in your text editor? Your first instinct might be to say use a string, right? For example, that's how you know text in any programming language. But then when you start to use your editor or you build it out, you realize that a string doesn't cut it anymore, because after a certain size and a lot of edits in your text or in your editor, you realize that you suddenly have a lot of memory allocations, edits get slower, it's not as handy to edit little things, and that's where more specific data structures for text editors come into play. For example, a rope, and there are others, gap buffers and other things to efficiently represent text in text editors or to make editing text efficient. And this is the scene that I just said. So now, looking at you, is everything I said correct? Is this why you would choose a rope, or what reasons are there?
Yeah, I mean, yeah, we chose a rope because it was sort of the proper data structure to use. But I don't even, our path to the rope was, yeah, it's very fuzzy. I mean, Rafe Levine definitely influenced it a lot. And we wanted a persistent data structure. That was another important thing, because in the Rust world, you're like wanting to go to background threads all the time. And so that was another really appealing notion of basically using a tree structure to store the contents of the text, is that trees allow you to do this path copying approach where you're recycling large pieces of the tree whenever you make a mutation. So it was those two things, like having persistence and then having really efficient, more than two things, I guess. There's the persistence, there's really efficient editing. And like the problem with a gap buffer is like, what about multi-cursor edits? Like, are you gonna have multiple gaps? Just isn't, as correct of a structure. But then there's also the ability to index. So all the time we're needing to make, translations between like rows and columns and absolute byte offsets. And we're also indexing other things like Unicode characters, like the number of actual characters versus the number of bytes. But I do think it's worth talking about the SumTree as well, because the rope is, an efficient data structure that's based on a tree for, storing and editing text. But we actually found that that same structure is useful for a variety of different types of sequences. Mm-hmm. And so really it's the SumTree that's kind of like the soul of Zed, I think, with a rope which stores text being only one instantiation of this data structure that's used all over the place.
All right.
But maybe it's helpful to talk about the specific example of text first, to kind of ground it before we generalize out. Yeah.
So here, let me set the scene again. Why do I have linked list open? Here, just for everybody watching this, the idea behind the rope is that you split up text into a tree. And you can jump in and correct me at any point here, okay? But that's the general idea, right? You have a tree representation of text, right? Smaller strings. You take a string like, hello, my name is Simon, and you split it up into these little chunks, and then you can, change substrings and whatsoever. So now, let's look at the rope in Zed. So we find it here, right? We have a separate crate for this. The rope crate, right? I think it's used by a lot of other crates, right? Or basically everywhere we have to do with text, basically.
Yeah, I mean, a lot of times it's used indirectly via another crate called text.
Yeah.
And then, then even on top of text, there's like the language crate that defines what a buffer is, which uses that.
Okay.
But
So
this is kind of the core of all that. And you can see that all a rope actually is in our world is an instance of this generic thing called a SumTree. But it's a SumTree of chunks of text.
So staying on this level, before we dive into chunks and SumTrees, what's the API? Like, what's a good example of how the rope is used, I guess? Is there any bit of code? Do we have tests in here, maybe? There you go. That's a good thing.
I think a lot of it is tested to the CRDT layer, which is in a different crate called text.
Yeah, there's a randomized test that kind of tests all the properties, I guess. But yeah, the main APIs I would say are push, append, and slice, and then everything else is like, I don't know, a variation on top of those. So the idea with the rope is that you can, like, the APIs are like append oriented, and this is in part due to the SumTree. Like, it's an append only data structure. And so it would be nice to find an example here that actually does something with the rope.
I think didn't we have something like just a simple rope and tests? Still finding references.
I mean, we can also just code it together real quick. So here, fn test basic. The main idea is like you can instantiate the rope. You can push a string and say, okay, hello, and then world, and then so this could be rope 1. Then you can have another rope, which is goodbye. I don't know, whatever.
Also world, yeah.
Also world, yeah. Moon, yeah. The cool thing is that, so here if you look at this, the text of this, is going to be like hello world, and the text of this is going to be good night, moon. But the idea is that then there's an operation. So push is already efficient, so you can efficiently append to the end of the rope. But the cool thing is that you can create a third rope by saying, okay, clone the first. That's also interesting. You can clone the first rope just by incrementing a pointer, essentially, due to the path copying behavior that Nathan was alluding to in the SumTree. And one thing you can do to this rope is append another rope, which is rope 2. And the result of that should be, this is rope 2. The result of that should be, assert rope text is the concatenation of those two pieces of text here.
Okay, so that's basically this is your one text, right? This is not two things. Like, this is mentally somebody who's not familiar with ropes could replace this with string, right?
Exactly.
Okay. And then here we build up two ropes, then we add them together, and the tests pass now. Sweet. All right.
There's also query methods. That we're talking about those. Like
let's do that.
And the cursor too. So to talk about how you'd implement sort of a
Let's go. Yeah, this is
non-trailing edit. Like, what if we wanted to take this rope, this last rope, and replace world with work or something like that. Like, we could sort of say let mute cursor equal rope.cursor, and then you can help me here. So you sort of say let prefix equal, and then you can kind of get sort of advance the cursor to a certain offset in the rope.
You start it at a certain offset, and then you can advance it to another offset.
So I'll just sort of for now say that I'll count manually. We're going to advance to the LD in world, and so that's like right now I've got. I think my prefix should be. This is a rope, right? That this thing returns.
That's right.
So I should say my prefix, as sort of an intermediate step, is hello war, Thanks, yeah. And then we can, now it's like, now that I've kind of reached the site of my intended edit, I can say, okay, I'm going to take the prefix and push, K, because it's hello work now, not hello world. And then I could say, but I still want the rest of the rope that's after the piece that I intended to edit. So I could say, what, prefix push. Well, first I need to advance the cursor past the piece that I'm trying to omit. Mm-hmm. So what do you do there?
I think
you
it's
say
seek.
Seek forward. Okay,
Mm-hmm.
and then I want to go... I guess I could sort of say prefix len +2, or I don't know how you want to express this to sort of for the audience.
I was just thinking,
yeah,
I mean, this is all
for me
subjective, but.
And then there's a convenience to sort of slice to the end called suffix, so I can say take the whole rest of the rope after what I kind of omitted and put that. And so now what we should be able to say, I'm going to rename this prefix because it's no longer just a prefix. I think it's called edited rope. And I think I needed to declare it as mute because I pushed to it. And then we could say what the edited rope should be hello. I think it's hello work good night moon, right guys?
Yeah.
Yeah.
If we did that correctly. So that's like how we model kind of edits that are not at the end of a rope.
Okay, so let's walk through this line by line here. So this cursor, can we think of it like a pointer? It doesn't allocate anything, right? You just point at a certain bit in the rope, right?
Mm-hmm.
I mean, okay. We could
Yeah,
also
reference
call it
into a
cursor.
rope plus the state that's needed to sort of remember where you are.
Mm-hmm.
Because the cursor under the hood, as you're seeking it around, like when you seek forward, it actually climbs up the tree and then back down. Or you can seek and it'll kind of start at the top and plunge down through the tree to the desired offset. And we're kind of summarizing information up this tree to help us efficiently find the particular offset you're interested in.
Okay, so then what does this do? What does the slice do? You start at the start of the rope, right? Which is at this point, it's this, right? That's in the rope. Hello world, good night moon. And then what does the slice do?
Slice is sort of, you give it a new offset that you're kind of advancing the cursor
Got it,
until,
okay.
and it's going to mutate the cursor to go there and then give you back everything in between where the cursor was and where it now is. So
Which is itself a rope.
It's kind of
returning a rope.
yeah, it's
Okay.
this mutable operation on the cursor that gives you back a result
Got it.
that it traversed over.
So this it's basically the substring, right? Like hello were here. But did this create a new allocation or what happened here?
It recycled pieces of the old rope that it could. There may be some, the rope is basically, the leaves of this tree are little runs of text.
Yeah.
I don't know what our chunk size is in tests. Hopefully at a size where this is actually exercising the rope with strings of this length. But in principle, you could think of these little leaves of runs that are actually basically strings, right? That are, contiguous chunks of memory that have character data in them. And so when you're slicing, any parts of the rope that are sort of wholly subsumed by your slice, we're going to recycle that part of the tree. And then we may need to construct new leaves for kind of where we have like partial overlap of a particular run of text.
So that's here, right? Like these are your chunks, right? Here. The hello, my, NA, I don't know. They don't have an even size, I guess. But
Yeah, and in our case, our rope is a little different than that because we're
Yeah.
using a B tree.
yeah.
So our chunks are between sort of base and base times 2 in size.
Okay. So then this takes out part of the tree that it can, but if you end in the middle of a chunk, you might have to create a new one that you take over. in your
Correct,
tree.
when that will allocate.
Right. Yeah.
But everything else won't.
Yeah, okay. And then this, I guess the push, this also goes to the last chunk, sees whether that chunk has hit the maximum size of a chunk, pushes in, or otherwise allocates a new one.
And, well, yes, although if there's another reference to the rope, because we're using this kind of copy on write model.
Yeah.
But we use a feature of Rust called arc make mute. It's a feature of the Rust standard library of arc, where you can kind of tell the arc, yo, I'd like a mutable reference to what you have inside of you. If no one else is, if I'm the only person that's holding a reference, then I can just go ahead and mutate my copy. I own it. But if there's another inbound reference, then we'll actually need to create a clone. So we do that optimization. So in this case, it will mutate because we're the only owner of edited rope. But that's not always the case.
Okay, and then seek forward. So at this point, we have this in the rope. You push this, so it's hello work. And then...
So this part, seek forward, is just advancing my cursor, which is a pointer into the old rope.
The old rope, right?
To a greater position in the rope. So it's like slice, except for it doesn't collect up the text that it traversed over and give it back to you. It's just moving forward the cursor.
Okay, so now you move the cursor forward in the old one, so you jump over the length of hello world, which could also be hello work. And then you take what's left, right? This is what this does. It says from the cursor to the end of the rope, suffix.
Right.
Right.
And the same principle applies where we're recycling as much of that tree as we can. And it's sort of walking up the tree, exploring this frontier.
Okay, so then this is what we end up with in the new rope. So before we dive in, what are the indexing methods that you mentioned? You know, there's like the...
Yeah, what are they?
Yeah, I think you can...
I'll loaded question. This offset, is it bytes or can you use something else? What else?
Yeah, UTF-8 bytes. Okay. Like the string is encoded in UTF-8, and so that's a UTF-8 position.
Okay.
But if you had a multi-line piece of text there, instead of those, is that true? Yeah, these methods are generic. In some cases, no.
I think the cursor, this cursor, likes to operate in terms of offsets. The things that are generic are the summarization pieces. So you can kind of say, okay, I wanna, in this particular range, I want to extract like a summary of this piece of text, right?
Yeah.
And that's the generic part. We have this notion of a text dimension, which is like literally a dimension of this larger summary that we capture. I mean, we can look at what the summary is. So if you go up, there is this notion of a chunk summary. And that is a text summary. There.
Okay.
So for every internal node in the tree, in this B tree, we will store this information basically.
There's sort of the length in bytes, the normal thing. But then there's some cases when interacting with language servers where we need to do references in terms of UTF-16 code points, which is like a different coordinate space. So we go ahead and index everything's length in terms of that. And then this is interesting. We use a point. So a point is like rows and columns. But what that's actually indexing is kind of, if you were to take the head of a typewriter, like the carriage of a typewriter, and walk it over the text, like the rows is sort of how many times it has to kind of carriage return. And then finally, the final columns is like the length of the last line. Mm-hmm. So that sort of summarizes, like in typewriter coordinates, like how long is this thing?
Okay. And why would you need first line chars and last line chars?
I think that's to calculate the longest row. It's basically a way to efficiently. I forget exactly how we implement it, but it's basically a way of being like, if you have two summaries that you're trying to kind of add together in the tree, in order to know what the length of the last line is on the first summary, well, the length of that is going to be the length of the last line of the left-hand side summary plus the length of the first row in the right-hand side summary. So I don't know how,
Yeah, the key idea is that like these text summaries, we summarize each leaf of the tree, right? But then like it's an index. And so what we're doing is we're adding up these summaries, we're aggregating them. In fancy words, the summaries form a monoid, an associative structure that's like aggregating up until we finally have a summary of the entire rope at the root of the tree. But if we're going to maintain some kind of guarantee that within that summary we understand what the longest row is, then we better be sure that it doesn't end up being a kind of the first row or the last row when they're added together. Like when they're added together, we might have split a line in half, but when we combine that together, it ends up being the longest. So
Okay.
yeah, we could even look at that code that does that.
Yeah, I'm right there right now if you follow me. This is basically a way to add two text summaries together. And you can see here, like, we're trying to track what the longest row chars are, right? And so, like, to understand that, like, one thing we'll do is just look at the summaries by themselves, right? It's like, okay, if this other summary's longest row chars is greater than ours, then great. But yeah, before that, what we do is we join the last line of that first summary and the first line of that second summary to see if that would become the longest row at that point. So yeah, that's a way, and the way that we use this information in the editor is to calculate what the longest row is so that we can approximate a scroll width for the editor without laying out all the lines.
Yeah, it's only an approximation because we only know in byte what the longest line is in terms of bytes, but of course characters can have different widths. You might have emojis and weird stuff in there, but it's never actually been a problem.
Okay.
And it's fast.
All right. So should we dive into the code here? Like what happens under the hood when we say, I don't know, we push something into a rope, right? We have an empty rope, then rope push here. I think I read through this before. This is
this
edge case up front, I guess, right?
Yeah, this changed a bit since the last time I touched it. So, but yeah. It seems like what we're trying to do here is try to fill up that last chunk as much as we can. Basically the logic is we're going to have a chunk, like the invariant of the rope is that every chunk in the rope is between base and 2 times base, right? Mm-hmm. That works, that invariant is upheld for every chunk except the last one because you may not have enough text to fill that chunk to fulfill the invariant. When we push, we try to take that last chunk that we have on the rope and try to fill it up as much as we can. Actually, what we do here is kind of more a little smarter than that because what we try to do is what we try to do is we take the text and we try to I think maybe this has changed, but what we used to do is we try to if you had a piece of text that didn't fit within the chunk, as opposed to just filling that chunk and then pushing the remainder of what was left, what we used to do was to kind of create a bigger chunk and then split that in the middle so that we would kind of balance out the size of the 2 chunks that would result out of that. I don't know if that's what we're doing right now.
Maybe we still do that in Append?
I don't
It comes into play when we're pushing a rope, right?
Yeah, there's this push large now. Yeah, I mean, clearly we haven't looked at this code in a bit.
Doesn't this just say if the new text fits entirely in the last chunk, then let's put it in. Otherwise, we
take
split,
it verbatim, yeah.
And then we keep track of, we just push this in the last chunk, keep track of the remainder, what's left, and then go into the normal.
Yeah. Yeah, that's right. Then there seems to be here a code path for large
optimization,
chunks.
But then basically here, new chunks. So we have a small vec, while text is not empty. We split it up into chunks on char boundaries, right?
Yeah, we will try to take chunks that are 2 times chunk base, but like sometimes those will fall in the middle of an emoji, for example. And so when that happens, we kind of backpedal a little bit and just go to the left.
Okay, here.
Yeah.
And then put them in chunks, and then chunks, parks, and I mean this is where we now dive into the SumTree world, I guess, right?
Mm-hmm.
I mean, what is chunks? Chunks is the SumTree, right?
It's the SumTree, yeah.
So let's talk. I don't know. It doesn't matter, right? Parks and let's do the non-parallel version.
I mean, yeah, it's gonna be interesting.
All right, let's start at the top. So the SumTree, where is it? Here is a B tree where each leaf node contains an item of type T, and each internal node contains a summary of the items in its subtree. Dimensions supported by a summary type can be used to seek to a specific location. So, Nathan, you mentioned it's a B tree, right? It's
Right.
It's actually a B plus tree.
Okay, thank you.
Okay.
But
Where the
in terms of,
information
like,
is stored in the leaves, whereas as a B tree, a classical B tree will store kind of a value also at internal nodes. But it's kind of an interesting B tree because the typical B tree is more of it's more designed to kind of have the typical B tree might be the Rust B tree, for example, where you have key value pairs, and the keys are let's say we used numbers as our keys.
Yeah.
Where we would store all of the key value pairs in the tree in their sorted order, and we would kind of be tracking up the tree what keys are in which part of the tree, so that when we're doing a query, we can kind of plunge down through the part of the tree that contains the key that we're looking for. In the case of a sum tree, and the reason we called it a sum tree, the leaves of the tree are actually containing quantities, and we're adding these summaries of the quantities up the tree. So it's a little different than the typical B tree in that it's summarizing I don't know. Can one of you guys articulate it more clearly?
Yeah. To me, it's the idea of the key is kind of similar in the sense that so the main idea with a B tree is that you have in a typical B tree, I guess, talking about our B tree, what you have is you store the summaries of all the children, right? So this lets you be I want to go in at position 30. Well, great. My child, the first child ends at position 10, so I can skip that entire subtree because I don't care about that entire subtree. So you keep advancing until you find a summary that contains the location you're interested in. Now, I think that idea applies to all kinds of B trees. But like Nathan was saying, the interesting idea I think of the sum tree is that typically in a key, in this example, when you have keys, what you would store is the maximum key for a particular subtree, right? For a particular subtree. Whereas the definition of what we summarize is kind of different in our world. We could as well store the maximum, but the idea is that we can store anything that is associative and works like a monoid. It's pretty tricky to talk about it in concrete terms, I feel but
let me. I'll try as a newbie to this. So with the B tree, how I know it from database indexes is you have a database index which contains the index, what you want to index, the IDs of users, right? And then you say, give me the user with ID 9, and you look at your tree here, and then you say, oh, it's between 7 and 16, so you go down, oh, here's 9, and then you have this, and it points to the user, right? But it's basically you walk down the index, and then you find the data. But the way I understand the sum tree is, as soon as you reach the leaves, meaning a point in the rope, right, or in the text, you also now know a lot about what came before, right? You know at which line you are, you know at which character you are, you know at what was it, UTF-16 offset, right? Because up until that point, you know the summary of things, or you know the the subtrees to your left, basically, you have a summary of those, and you know how many lines are in that. And in your little subtree, you can go up and calculate how many lines are in yours. Is that kind of capturing this?
Yeah, another way of thinking about it is it's indexing like a running total. So like a really simple example, like we can even play with a sum tree. We may have examples in the sum trees test where we're
Let's
like
see.
indexing test. Yeah, that one's too
Here, what
complicated.
is this? Test cursor, empty tree?
Yeah, this is
Yeah, there's this integer summary, which is an example of a summary that we could maintain
Right.
of these integer items.
so in this case, like we have a sum tree of U8s.
Oh, I see. Interesting.
And so, like, the basic idea is like, if you can imagine a list of integers, those lists of integers have like a total that's accumulating as you're adding them up. But what the sum tree would enable you to do is be like, at what count of integers do I reach the total 100? Or you could say, at the 20th integer, what's the total of all of them added up? And you could answer that in big O of log n and the number of integers time.
I think
so
this
we
is a
could-
good example, right? Like if you, I don't know, say you have 30 integers and you go to the 25th one, whatever, and then this index allows you to answer, oh, does any number up until where I am contain an even number?
Yeah.
Right? All of the 24 previous numbers.
Yeah, that's another property you can index.
Yeah, right now, the way it's structured right now, I don't know that you could do it precisely like that, I guess. But yeah, you could do that. I guess the sum tree would allow you to do
I
that.
think you.
Oh, it does. Yeah,
you can
your
seek to
summary
that.
contains even. We have that. We're indexing that.
Yeah,
Yeah.
that's what I mean here with this contains.
Oh, but you're saying, I get what you're saying though. Yeah.
So if you started your cursor at the beginning and then you asked for the summary up until number 25, it would return a summary that is this struct right here that would tell
Yes.
you, does that slice of the sum tree contain an even number or not? And
That's
so
valid,
that'd be
yeah.
like a logarithmic way to answer that question.
You'd also be able to ask what the max is in there or what the sum of all of them is in there.
Yeah.
Anything that aggregates, you can index.
You could seek to the first even number if you. I mean, I don't know that we'd have to add a dimension for that.
Yeah,
but
exactly.
Yeah, it's kind of interesting that we should talk about the dimension trait and how that's structured because it's a
Okay,
cool way
let's-
of modeling these different questions you can.
Let's do
ask.
that. Let's jump back to, we had this test, right? Test cursor. So just to start here, we basically construct a sum tree of U8s, and then where does here we say we want a cursor with this type of summary, right?
Yeah, this is a really boring test because the sum tree is empty. So
Okay.
it might be a little more interesting.
Here,
to
there's one element in it. If this is more exciting,
Let's come
There we
down
go.
here.
Yeah, here's the bottom. Yeah, same test, but a new passage.
Well, I'll
new part
follow
of it.
you. There
I
you
just
go. Okay.
I just scrolled down like 2 paragraphs.
Yeah.
So it's like, basically the sum tree. Just to recap the type structure is like the sum tree is generic over a T, which is the type of the elements in the sequence, and then there's an associated type to the T, which is how do I summarize the T? So that's T summary. But then there's more to it than just that because you can, for a given summary type, right now for this sum tree, we have this integer summary that has these 4 fields. You can sort of choose to kind of seek in different ways over it. So there's this type called a dimension that's like that represents like sort of an aspect of the summary that you want to keep track of on your cursor. Right,
What
guys?
does
So
that mean? Can
like-
we look at the dimension, or is that too generic to make
yeah,
sense?
I think we can look at the dimension.
There you
It's
go.
pretty straightforward. Basically, you can think of it as like a subset of a summary that you're interested in for a particular query.
Got it.
And so it's like,
Here, Zed's rope has a text summary type that summarizes lines, characters, and bytes. Each of these are different dimensions. So, number of lines, characters, longest lines, and whatsoever. These are the dimensions.
and the idea behind it, I think, is that like if you kind of think about a given query you wanted to do over a rope, you might not need to like often it's going to involve a cursor, but you might not need to count the points or the longest lines or certain aspects of the summaries to answer your question. Like if you're just seeking to a UTF-16 offset, you can have a cursor whose dimension is UTF-16 offset, and it'll kind of look at each summary and pull off the UTF-16 offset and sum those in order to sort of let you kind of seek to a certain UTF-16 offset. But in it's the cursor has state that it's like stack based, that tells you where it is in the tree, and you can make a cursor that doesn't, just for efficiency reasons, doesn't sum up all of the summaries in their entirety.
If I had the text, where was the text summary? It was in the text summary. So this has, what is it, 48 bytes, right? Text summary has a bunch of fields. So what you're saying is, if I have a rope and I'm only interested in lines, for example, what line am I on? I could basically traverse the whole rope and the cursor, like seek along the whole thing, and the cursor would only keep track of this one dimension of it, the point, and it would basically not, like, how many bytes is this? It's 8, right? It would only accumulate like this and not the other fields because you're not interested in that.
That's right. And as it stepped over every summary, we looked at that add summary routine, or it was called add assign, that's about combining two. It wouldn't perform all of that addition. It would just perform the subset that's defined in the dimension trait that is sort of adds a portion of the summary.
Okay. All right.
Like if you jump to me, like there's an example of where we're saying offset UTF-16 is a dimension. So given a SumTree whose basically summary is chunk summary, we can define a dimension over that summary that is defined as such, and it's pretty straightforward, right? Like the UTF-16 length out of the summary and focusing in on only that one piece. It's interesting that in the particular test we were looking at, I don't think our cursor was taking advantage of that use case.
We sort of have this blanket impl that you can just use a summary itself as a dimension if you're interested in the entire thing, and that's what we're doing here. But I was sort of going into that because you noticed that there was this type parameter. I thought, Thorsten, you commented on that this cursor method takes a type argument, and that's what the type argument is. It says, what does this cursor right now want to kind of, what dimension does it want to keep track of the summary? And so in this particular case, we're saying take the whole summary, but you don't have to. You don't have to do that.
Okay, so this could just be a dimension of this summary here.
Or it could be a tuple of 2 dimensions.
Yeah.
We do that.
This example is showcasing is, and the tuple I think is another example of it, is notice how the cursor is generic over the summary, but still we're able to seek in a dimension of that summary. You're seeking, we're slicing actually using count.
What is count?
So this basically highlights the ability that the cursor has, that you can seek in a dimension but aggregate, in another. Meaning, imagine you want to convert from UTF-16 to UTF-8. You want to know, I want to convert, UTF-16 to UTF-8. Well, one thing you can do is create a cursor that aggregates both dimensions, so both UTF-16 and UTF-8. Seek in one dimension, so seek in UTF-16, but in the meantime, aggregate what the corresponding UTF-8 location is at the same spot. So you can very efficiently, convert between the two.
So in this case, when you said what is count, it's literally what is the total, we're just counting up the integers, right? So when we slice to a count of 2, you can see the result that comes back from that is 1 and 2, the first 2 integers in the list. So that's where we're parked. And then
is count a dimension? What is?
Yeah,
here,
let's look at it.
I'm at the impulse of count.
There you go.
It's actually it's not just that there's summaries and dimensions. There's actually 3 kind of generic. There's like Antonio was mentioning, there's a third associated type called seek target or trait. So it's you your sum tree for a certain type of item, there's only one sort of summary type. There's a certain thing that when you build the sum tree, you are summarizing. And then when you make a cursor over it, there's a subset of that you can aggregate. And that's the dimension. And then you still have more flexibility. You can, even if you're aggregating, a given dimension, which is a given subset of a summary, you can still seek to another type called a seek target, which is like often sort of a subset of that, or is like something that's comparable. Basically, it's a type that is comparable to a dimension value. And that's why the trait, when you see the impl of seek target, it's about comparing to a dimension.
So the count, let's look at how we summarize. Where do we define that? Here. So here, in order to be an item of a sum tree, you have to impl this item trait. And so here we're going to be like, okay, I want to build a sum tree of U8s. How do I do that? Here's what it means to be a U8. We have to define how to summarize one of those items. And so in this case, the count is going to be 1, right? There's only one integer. We're summarizing one integer. And then the sum is like the actual value of that integer. And you can see here, when we're adding the integer summaries together, we're just adding the counts together. And so basically the count dimension or seek target is kind of a way of indexing by as if it were an array, right? You're sort of seeking to a certain total number of items. But then once you're there, if we go back to that, is somebody in that test that can jump back? Or let me use the history here.
I think it was test cursor, right? Test cursor, and then
you can see here we're where does the cursor start, right? And that's going to basically give us a reference to the dimension that the cursor is defined over. And so then we can ask, what's the sum? And so we can see the sum is 3 because the sum of 1 and 2 is 3. So the count, first two integers sum to 3.
Okay. So here it says I'm on 3, right? The previous item is this, 2. Next item 4. The sum until now is 3. I mean, it's, if this was 99, it would still work the same way, right? And then the sum would be plus 98 here, right?
101.
Yeah. Okay, that's cool.
Yeah, one interesting thing is that, still speaking of the differences between this and the Rust B tree, is that in a Rust B tree, what you do is you can just insert a key, and the data structure takes care of inserting it at the right spot for you. Whereas in our world, the tree is an append only, meaning you can only push to the end of it or append to the end of it, and you're responsible for putting items in the location that you want to. The data structure doesn't take care of kind of establishing, an order. We have a specialization of SumTree that defines a map, like the B tree map. But yeah, SumTree per se doesn't, you need to decide where you want to put your items in the tree.
Everything is framed in terms of a running total.
It's not conceptually a map. It's more like a vec that has these special indexing features where you can store any sequence of items you want. You decide the order, and it just provides these capabilities to seek and slice.
And so we use it. Oh, go ahead, Thorsten. Sorry.
So if coming back to the start, text editing, you represent the text in an editor as a rope, which is a sum tree under the hood, and then I put my cursor right in the middle, and I want to insert some text. Then we would have to do the thing that we did in the test here, right? In the what was it? Test basic, right? We would we would have to seek to that where the cursor is, right? And then we would then have to insert something. But the sum tree doesn't give you, you need to point it to where you want to insert stuff, right?
Yeah.
In this particular case, what you would do is you would slice up until the point that you want to insert at. So you would take that prefix, add your new character, and then append the suffix of the cursor.
And what's cool about that is it generalizes really well to a multi-cursor edit where you're making hundreds of edits, and you don't want to do hundreds of random logarithmic accesses into the tree. What the cursor lets you do is sort of start at the beginning, go to the first edit, then the next, in an efficient way via kind of one walk of the tree and sort of perform the slices that you want.
And because we're recycling bits of the old tree, right? Like when we're editing, we're actually building a new tree.
Yeah.
And so that way, if there's some process running in the background, like tree sitters parsing or anything else that might be going on in the background, it still has a reference to the old tree. You've kind of recycled bits of the old tree, but you haven't changed it.
That's important for multi-threading, right? Because I want to set this. See, did I lose it? No. There was this article here, Text Showdown. Let me open this. This pretty famous article, I guess, in the Rust scene where they were comparing gap buffers and ropes, and somebody's rewriting Emacs and saying gap buffers aren't that bad, and then people were saying, yeah, you should optimize for use case. But then at the end, he mentions this, that, basically he said like, oh, the multi-cursor is doable with gap buffers, other stuff also doable with gap buffers, but ropes have other benefits. Both Crop and Ropey, which are these Rust libraries, they support concurrent accesses for multiple threads. This lets you take snapshots and do asynchronous saves, backups, and multi-user edits. This paragraph doesn't...
End of showdown. Yeah. It matters more than any of that other stuff. Yeah, no question.
Yeah. We use that all over the place. And we also have like other SumTrees, right? Because like when you think about, when you're editing the buffer, you're not actually editing a buffer because like what you're seeing on screen is a transformation of what's in the buffer. Because the buffer represents what's in the file. But like, what if you folded? Or what if there's soft wraps or tab expansions? There's all these like layers of transformations that are going on, all of which in Zed are indexed in this stack of different SumTrees, which on every edit, we're sort of rippling the edits through this stack.
What?
Doing bookkeeping.
Can we look at one? Like I know we're coming up on time, but like what's an interesting other use of the SumTree?
You have inlay hints enabled right there, right?
Yeah, inlay hints, right. There
so like those things don't exist in the buffer. So yeah, those are modeled as a map called the inlay map. So if you follow me, I'm right there. And all these maps are kind of very similar in that what they are doing is kind of modeling this sequence of transforms. Between like some input text and some output text. So in the case of the inlay map, you would have, say that you have an inlay at position 5. This tree would model like an isomorphic transform for the first 5 characters of the SumTree. So like, it would be a transform that that has the same coordinate space in input and output coordinates, right? Like it's not changing anything. Then you would have a transform. Oh, go ahead.
Just to jump in, for everybody who doesn't know, not me, obviously, what's an isomorphic transform?
Same shape.
Same shape. Yeah, exactly. Like it's 1-to-1, right? Like you're like 5 characters go in, 5 characters go out.
Identity.
Right. Yep. Sorry. Yeah. Isomorphic is pretty, I don't know, jargony. But yeah, so in the case of an inlay, so you would have this initial identity transform of the first 5 characters. Then you would have another transform, and we can see here that would model the inlay. So it would map, say, like 3 characters of the inlay to like 0 characters in the input, because the buffer doesn't really have those, right? So 0
we should look at the summary. Like, let's look at the item implementation for transform.
Does that mean if I have a text
transform summary here? Yeah, I mean.
You have text, say 10 characters, then you have an inlay hint, then you have 10 characters, inlay hint. That's a sequence of isomorphic inlay hints, isomorphic inlay hints, and that sequence is also modeled as a SumTree, so you can say, okay.
That's correct, and like that's what lets us do all those, lets us map from display coordinates, so what you're seeing on screen, to the actual buffer. Again, we use the same technique as before. We will. If we want to know, where the cursor is in buffer coordinates, we will start at the display coordinates, like seek in that dimension, but in the meantime aggregate in the buffer coordinate space so that we can map back and forth.
And
And
that's
this is happening through like a few different layers. Like if you look at the display map, that's like the top of it. Although I mean, here's all the different,
Yeah, there you go.
you follow me. Like, there's a lot of different layers, each of which is sort of a similar transformation sum tree where we're indexing input to output, each kind of built on the layer below. And so when you're typing, we're basically cascading your position through each of these to figure out where the hell are you actually trying to edit in the actual buffer, which is not where your cursor is on screen.
So how do these build on top of each other? I understand like the inlay map, you start with the normal rope, right? Which I guess is somewhere in the buffer. And then on top of that, I mean, is it even correct to say on top of this?
Yeah, I mean, I guess multi-buffer is another layer actually, but maybe we can skip
But
that for
let's
now.
ignore this. But say you have a
Okay.
buffer with text, and then the inlay map, what does it do? Like it builds an index?
Let's look at it. Yeah, let's look
Look
at
at
it.
to offset here on display map is like
Oh, yeah.
one
Okay.
place. Or no, is this right? Yeah, because this is a
yeah.
display point, right?
Yeah.
So if we want to convert a display point to an offset in the buffer, what does that look like?
There you go.
And so you can see here we're gonna, we're taking the block snapshot first, and we're gonna convert the display point to a wrap point, and then the soft wrap snapshot, we'd like take the wrap point and go to a tab point, and then the tab snapshot, which is responsible for expanding these single character tabs to 1 to n characters depending on what column they're in, blah blah blah, right? That goes there, and then we go through the fold snapshot, which accounts for the fact that pieces of text may be hidden, and finally we get to the inlay point, and then we go through that to finally get the place in the actual buffer where the display point, which is this object here, corresponds to byte-wise.
So these are all sum trees under the hood.
Yeah.
Except for the tabs one.
SumTrees are the soul of Zed, like I told you earlier. Like, they're everywhere. We also use them in like other places in the UI, but that's another,
Yeah. I mean, even the get blame feature, right, that we added here, like all of this information too is under the hood is a sum tree. It's just which blame information do we have at which line and whatnot. Which is, I don't know, wasn't me that came up with this, with Antonio.
After solving it like
After
8 different other times.
writing 2 billion times,
Yeah.
everything looks like a sum tree if you squint.
So we're coming up on time. So to zoom out a little bit, just briefly touch on this, right? Like memory, performance, space-time complexity. Like how did you balance these trade-offs? And again, loaded question, but I think what we just talked about with this blog post here, that the rope and the sum tree allow you to have snapshots, to allow you copy on write, to easily pass stuff to other threads. That was, I guess, one of the big, decision points here. Or did you try out many other text data structures and then ended up with this? Or
SumTree was like the first thing that we almost created. Like I remember like I think it was 2017. I was like working on the SumTree on my couch. We were watching The Crown. Yeah, I remember. Yeah, so that was like some of the first code when we were like, let's build let's do this in Rust. When contemplating like starting over with Atom, like the SumTree is sort of where it started, and it started quite a bit simpler than it has evolved to, but like some of the oldest code in Zed is part of the SumTree.
Cool.
We also did CRDT in the SumTree, right? Which is a whole other
yes, that's
topic.
another episode. We
Yeah.
can fit that into 1 minute.
Yeah, because we have 1 minute left.
All right, then thank you so much.
Thank you.
Bye, everybody.
Bye.